start on that. So we are going to abbreviate random variables with by RV in lowercase small letters, right? So this is a very important concept in probability, right? It allows events to be viewed as something that spit out numbers, right, and how to manipulate these numbers and so on, right? So it's so important that, right, the whole theory, you might say, is built around this concept of random variables and how to generalize from that, right, to how to build bigger things, right. So we start with the most fundamental thing first, right, and continue from there. So let me begin this by asking you people, what some of you have seen this before, what is your what do you say, what is your idea? I am not even going to call it a definition. What do you understand by the concept of random variable?
Mapping of sample space onto the real line.
Okay, the mapping of a sample space onto real line, fine, that is one very mathematical or somewhat mathematical definition, but what does it physically mean?
Outcome of a random experiment.
Okay, instead of saying outcome, we will say output, right, because outcome can be any of the omega I points which are more general than just a number, right. So outcome, with that word or that term we reserve, right, for what we see in the random experiment, which can be more general, right, which need not be a number, but the numerical output which is somehow, right, measured, and there can be more than one numerical output also. So one numerical output, right, that we can measure or we get somehow from a random experiment is called a random variable, right. So that is the English, right. What is this? These are models for numerical output So having said this, now we will go to the formal definition, which some of you have obviously seen, having taken earlier subjects in this, earlier courses in this topic, right. So we will, for now of course we are going to restrict our omega to be discrete, right. All our considerations until I make a departure from this is only going to focus on discrete omega, okay. But the idea of course is more than just is applicable to more complicated, I mean the continuous or uncountable case also, right, but let me just state the definition in terms of the discrete omega for now, okay. So a random formal definition, and a random variable is a mapping what does this mean? So i.e. a random variable is a function, right, it map, right, the it refers to random variable, the it associates a number, a real number for all omega I in R. Now I can say omega I because I have said, sorry, all omega I element of capital omega. So I can use omega subscript I because I have said that the space has to be discrete, right. I cannot use, remember, an I to index a sample point if the space is not discrete, right, if it is continuous or uncountable, okay. So it's a mapping. So it has to be applied to every omega I. So mathematically what we have, notation for random variables, let me say that also up front, we use capital uppercase letters, right? And of course we will need subscripts, right, like 1 or 2 if you have many of them, right. Remember, you can define more than one random variable on an experiment, that should be quite obvious, right. It could be, I mean, simple examples where the omega is more complicated than just some numbers would be picking up individuals at random from a fixed population, right, where you have, let us say, each individual corresponding to one of the omega i's, right. How many numbers can you associate with an individual? As many as you feel like, right, you doing, as many as that make sense or are useful, right. You can measure heights, you can measure heights are less controversial than weights. Weights can turn out to be somewhat more controversial because of other problems, but anyway, and you have blood pressure, but blood pressure at a given time which varies, right. So we are saying that it's just a number, right. It's not going to be a function as of now, right, or anything more complicated than just right. So at the beginning we are just looking at numerical outcomes, or sorry, numerical output, right. So the random experiment itself throws at you an outcome, right, and you map that outcome to a number, to a numerical output in more than one way, right. So one consistent way of mapping is one random variable, like the set of all the heights, right, or all the values that the height random variable takes in an experiment, right, things like that. So I don't think, I mean, it's a fairly intuitive concept, and I hope that I don't have to spend too much time verbalizing it, right. This is okay so far. We are just mapping. So this notation we will use. So supposing I take x is a mapping from omega to r in a more general way, but we can tighten this, the range. R is a set of real numbers, right. So this is the r in general, we will write r because we are not going to write, as of now we don't know what else to say. We get right, but you might say, why should it be r, why can't it be a smaller set? Well, there is some merit in that, we will see, right. Especially for a discrete space, it turns out that this r is a little big. You don't definitely cover all of r for any discrete omega by any random variable, right. But this notation, this mapping notation is very important. The argument of the random variable is always the omega for that experiment, right, the sample space of the experiment. And so you should look at the output of the random variable as a number. So the random variable is just a name that says, it refers to any of the possible outputs, that from what set, from some set, a set that has to be defined carefully based on all the mappings that you have, right. For example, if I toss 2 dice and say that, right, then the output that I am looking for is the sum of the numbers on the 2 dice. I obviously don't, right, expect to get some crazy real number like pi or e from that experiment, right. So we have actually the collection of outputs, especially for a discrete space, is highly limited by circumstance, right. You don't have all of r or anything like that. In fact, you can obviously see that if omega is discrete, right, the collection of possible outputs is also countable. It cannot be uncountable, right. So what is the notation I am going to use? I need one more notation to keep things straight, right. Instead of r, I am going to say, well, let omega x represent the collection of all possible outcomes, outputs. And that I am going to write as all possible values of x. The mapping x takes values in this set omega x, right. So we say that x takes values in omega x, right. That is going to be the terminology we will use throughout, right. Any random variable will take values in its range space. So this omega x is the range space of the random variable x, right. So that is the range of x. So instead of saying that the range is R, you can think of x being a mapping from omega to omega x. And since I want, something like omega on the right side here, because it is a universal set as far as x is concerned, right. X cannot take values outside of omega x. Whereas this omega can be some abstract space, this omega x is always a subset of R. Is that clear? This omega x is, and not only that, for any discrete space this omega x must be a countable subset of R, it cannot be suddenly become uncountable, right. So omega x will be of this form, right, where xi can be capital X. So just to cut a long story short, I can write my omega x like this, right. And of course this is valid, right, this kind of statement is only valid for discrete omega, not continuous or not uncountable omega, right. So that I do not have to draw any more pictures, I can just write it like this. But if you want to visualize this as a picture, you can draw this capital omega on one side, you can draw the real axis here and do some mapping, right, but maybe I will do it since I am being recorded. So whatever, so we will draw the right real axis vertically rather than horizontally, just to make it easy to show the mapping. So you have omega 1, omega 2, whatever. Note of course that this, you can have a countably infinite collection of points here, there is nothing to stop you from doing that, right. So you have this map to x of omega 1, which is some small x1, and there is again, right, no the only rule is that each of these points must be mapped, right, to a unique point, must be mapped to some point out here. So you can't map this to 2 points here, that for given one random variable there is no way that by mathematically you are prohibited from saying my x of omega, capital X omega 2 is both x2 and x3 or something like that makes no sense. But you can have multiple points out here omega I mapped to the same x, that is perfectly okay. In fact that's what happens when you say that, for example, that the x is for a pair of dice is the sum of the values of the 2 dice, right. If you had 4 3 or 3 4, in both cases you are going to map it to 7. So you may have 36 values here, 36 points here, the cardinality of omega, this capital omega is 36 in that case, right, for rolling a pair of dice. But this is much smaller, you can go count the number of points that you can get, right, you can get only 2 to 12, isn't it, integers from 2 to 12, okay. So anyway, and these points do not have to be integers, they can be some real numbers, right, there is no reason to insist that they must be, in fact that is not at all, right. I can divide by square root of 12 or something if I want to do something, right. I can say sum divided by square root of 12 or something, or pi times the sum of the numbers, right. So I can get real, what can I say, God given real numbers on this axis, there is no reason to restrict it any further, right. Okay, so I have omega x as being this collection of points, right, and whenever the outcome omega I occurs, the random variable x spits out the value x of omega, capital X omega I, which is written as small xi, right, and the I index is only, whether it indexes basically either something here or something here, but you have to be careful that xi, note that some xi can be some equal to some xj. If you write it like this, it is possible, if you write it like this, it sort of implies a one-to-one mapping, which need not be the case, right. So if I write it like this, omega x, but here we will avoid duplication, right. So there is a subtle difference between these two. Here there is no point in repeating the xi twice, you only write it once, isn't it. So there is a small difference between these two, but it's okay. I mean, we can't be in just writing it in some simple fashion like this. I can't be too mathematically rigorous and say, well, I want to make sure that I can I want to avoid all of this here and so on, right. As long as you get the point, right, we will go ahead with this, right. We are not going to keep using this notation too much. In fact, I will probably not come back to this anymore, right. We are just going to in fact suppress this argument when we use the capital X, the random variable. That's the way it's always been written. You say the height of somebody or the number you just say the sum of the pair of die so when you write it, you just write it as x, capital X, when you refer to that random variable. You don't put capital X of omega anything, right. So it's like saying f is a function instead of saying f of x is a function, right. So this notation omega x is something which again we don't have to keep on reminding ourselves about it all the time. As long as we know what it is in some in the beginning, you can you don't have to keep coming back to it, right, that whether this x4 is equal to x1 or not, right. It's so here usually we don't avoid right, no, duplication is not done. Just for the sake of completeness, I am saying this, right, nothing else. Okay, so let's look at the most important concept or the most important property induced by this mapping, this x. So you have what is called the probability mass function, right. What do you understand by this? This is now going to say how we can manipulate just only a random variable x without worrying about the underlying space from on which you defined x, right. So this is going to be given omega I, we have x of and xi element of omega x. So I can now talk of the probability that this capital X equals one of these points in the set, right. So that is a problem. When I do it systematically for all the points in omega x, I get what is called the probability mass function for x, right. Is nothing more or less than just this, just p of x equal to let's xi, right. That's right. What is the probability that x takes the value small xi, right. So you can call this as some pi, right. And note that I am not going to put any rigorous or whatever limits on what I should be right, or anything. I am just going to say I can be any positive integer typically, right. So that this probability, why does it make sense? Because so given some, if you have omega I, right, and it has a probability, obviously this event has a probability. So x equal to xi is an event. Note that it is an event. Why? Because our event space for a discrete omega is a power set. So any such thing you say on omega or right, any combination of omega i's, any union of those omega i's is an event, right. So this has to be in one of those events, right. I can have at the maximum some numbers here mapping to the number small xi. So what does this mean? This x equal to xi means I got either omega 1 or omega 10, assuming that omega 10 also mapped to that xi or omega whatever, right. If I have some 2 or 3 points mapping or more than that, whatever, all those, any one of those points will give me this event. And so what is the probability of this? So i.e. the probability of x equal to xi will be a sum of what? P of this remember we start out for a discrete space by assigning probabilities to all the sample points omega I. So you are going to, again it is very similar to some earlier notation we wrote, we are going to add it over all those points such that omega I such that x of omega I equal to xi. So everything here, all the xi's now are numbers, right. Earlier we had more abstract events, we wrote some such thing like this, right, except here now instead of calling this some event A, we are explicitly writing the event like this, x equal to xi. Otherwise there is no difference between this and any other event that we saw earlier. So here we are looking at those points omega I such that x of omega I is xi. So in fact this is, you can say this you know, you can always go back to this, right, that for every omega I there is always some xi, one unique xi for every omega I, right. And of course keep in mind that you can have this kind of thing also, that is all. Once you are ready with this, then this does not really this is only written for convenience in some sense. You do not really need to worry about, oh my god, what is my omega x for this experiment. As long as you have done this mapping correctly, right, this will also almost follow suit by itself, you do not have to worry so much about it. It is just nice to not have to worry about all of R. This is the only reason I am bringing this notation omega x is to tell you that you do not have to, for a discrete omega there is no reason to worry about all of R, there is no way you can get that. So this is, I mean even conceptually, so this is, it is nice to know that you, right, you are never going to go outside of some countable set omega x, that is all. Otherwise, right, you are only interested in this. Is this okay, or you have a question here?
Sir, is omega I like disjoint?
What did we, when we started the whole thing, we said only one outcome can occur at any time in any trial of an experiment, right. So obviously the omega i's have to be disjoint. They are, if you go back to the first or second lecture I said they are mutually exclusive, collectively exhaustive, right. That is how you think of capital omega and small omega i's, right. So obviously, I mean omega i's have to be disjoint. If you get 3 4 on a roll of die, you do not get 4 3, you only get 3 4. Remember, right, the ordering is important. So in other words, especially in the discrete case, it turns out that all these pxi's are typically positive numbers between 0 and 1. So this is usually greater than 0 typically. So that is the significance of all these numbers here, that they all have, under the mapping x, all these numbers have positive probabilities, right. And not only that, the sum of all those probabilities has to be 1. So how did I, okay, P of x equal to xi over all I. So here again, as I said, the definition of x of the I here, that is why I am not saying I going from 1 to 5 or anything, I am just simply putting, this means adding up over all I, this must be equal to 1. If you add all these probabilities, here you are adding only, right, you may not be adding anything here, if there is a one to one mapping between omega and xi, there may not be any addition at all, but here you are adding, right. So what is a PMF then? The PMF is basically the, right, it is not just the P of x equal to xi, it is also the xi. So the xi, the collection of points xi and the probabilities are together called the PMF of x. Okay. Now this is a bit cumbersome, right. So we will write it, we have said we call it PI sometimes, or a better, a more common way of writing it is to say, you write it like this, put a small p here to distinguish it from this capital P, right, because we like to use small lowercase letters also occasionally, right, but the uppercase letter is always used for the random variable, right, and the random variable will come as a subscript, because you want Px, if x and y are two different random variables defined on the same experiment, right, their PMFs are going to be different. So you have to have some notational difference between them, and we get that notational difference by subscript, right. You put Py for the PMF of y and Px for the PMF of x, right, and so this probability you write it, well, sometimes you may write it as Pi for short, but if you want to be more explicit about the role of x, you must write it like this, right. So in other words, you can think of a PMF as splitting again this the cake of volume unity, but instead of saying I want to divide it among some right abstract points omega I, now I am going to pick some bunch collect a countable set of numbers from the real line and give it only to those real numbers, that is all I am doing, right. So I need to keep in mind both the values that the random variable can take and the probabilities in each of those points. So that is how I generate PMFs.